Towards the end of yesterday's class, we learned one basic mechanism of deriving the first order differential equation, and we said that we will define the new set of coordinates as P I, which will be the derivative of the Lagrangian function with respect to Q I dot. So, that is how we defined it, and then if you define this, then the derivative time derivative of this term is nothing but P I dot. So, your Lagrangian equation becomes became P I dot minus derivative of the Lagrangian with respect to Q I plus derivative of the Rayleigh with respect to Q I dot is equal to 0. We would normally express it as P I dot is equal to derivative of the Lagrangian with respect to Q I minus derivative of the Rayleigh with respect to Q I dot. So, you see here is the dotted term, and the right hand side will have to be expressed in terms of the undotted terms, right. So, if you want to derive the first order differential equations of any system, essentially you would need to write Q I dot is equal to something and P I dot is equal to something. Now, P I dot is equal to something that is obtained from this equation, and Q I dot is equal to, how do you get it? How do you get it? You will actually get it from this. Let me illustrate how. Let us start with you have already done the spring pendulum system, right. You have already the Lagrangian written up. So, let us start from there. So, the spring pendulum system was and we had defined the A plus R, yes, where A was a constant and R is a variable, and in its term we had already written the Lagrangian as this. I will not derive all over again, I will simply write it was half m r dot square plus half m A plus R square theta dot square minus half k R plus m g by k square plus m g A plus R cos theta minus m g A, that is how it was. Okay. So, this is the Lagrangian function, and then we know that the P I is the derivative of the Lagrangian with respect to Q I dot, which is in this case R and theta. So, we will write P 1 is equal to derivative of the Lagrangian with respect to Q 1 dot. So, Q 1 was R. Okay. So, it was okay. It will be convenient for us to in order to proceed, we will say Q 1 is equal to R and Q 2 is equal to theta. Okay. So, this is, let us write things in terms of Q 1 and Q 2. So, this is m Q 1 dot, right. So, that is the in the first coordinate the momentum, and in the second coordinate the momentum is is it has to be done with here. So, it is m a plus q 1 a plus square into q 2 dot. Okay. So, notice that you have independently obtained the momenta in the two directions, right. Now, writing the differential equation. So, this equation will give q 1 dot, the dotted term in the left hand side is equal to, that is it, and this will give is fine. So, you see, out of the 4 equations that you need to derive, 2 were simply obtained from this. Now, to the other 2. The other 2 would be where P 1 dot is in the left hand side and P 2 dot will be in the left hand side. So, that will have to be obtained as this equation. This equation, in this case the r term is not there. So, only this much. So, we will have to write P 1 dot is the derivative of the Lagrangian with respect to q 1, which is something that we had already written up. So, it is one thing. Now, it has to be done in terms of in the right hand side, things have to be expressed in undotted terms. In the right hand side, things will have to be without the dots. So, just keep that in mind. So, here we have already written down the derivative of the Lagrangian with respect to q 1. So, write it in the right hand side. Right. So, I am yet uncomfortable with this term, because here I have a dotted term which I do not want in the right hand side. So, that can easily be eliminated by substituting this. So, that gives finally the equation. So, it will be this q 2 dot is p 1 by m. So, 1 m will cancel off, it is p 2 square here by m, and then it will continue a plus q 1 minus k, all these other terms are without dots. So, sorry, yes. Cube. No. No, it will remain, yes. So, this is m g by k plus m g cos q 2, fine. So, we have obtained one equation, one first order equation without any dotted term in the right hand side. Have you seen the technique? So, the first point was that in this problem we had the Lagrangian already derived. We said that let q 1 be r and q 2 be theta, and then your p 1 is derivative of the Lagrangian with respect to q 1 dot, which yielded this. So, that directly yields q 1 dot. as one first order differential equation. P 2 was this that directly yields the Q 2 as a first order differential, Q 2 dot as the first order differential equation. P 1 dot then is obtained from this equation, and in this specific problem, this term being 0, it is only this much which we wrote down. We had already derived this right hand side, this one, but here a Q 2 dot appeared, which should not appear in the right hand side of a differential equation. So, we substitute Q 2 dot from there, and then we got the final equation. Similarly, P 2 dot is, it is the derivative of the Lagrangian with respect to Q 2, which is you have already have it, it is minus m g a plus q 1, yes, it does not have a dotted term in the right hand side. So, we are through. Do you see the 4 equations? So, this is how the first order equations need to be defined if you are obtaining it from the Lagrangian equation. Clear? Let us do one problem, one circuit problem, so that you are little more comfortable with it. Let us see, let us circuit like this. Oh, notice that if we did not derive or did not define the P i's this way, then all this will have to be obtained ad hoc, and getting rid of the dotted terms in the right hand side would not be so simple as this. That is why this is a systematic procedure of doing that. That is why the position and the momentum, these are taken as the conjugate variables always. Okay, so, here is E, here is C, L 1, L 2 and R. How will we go about it? First, we will define the charges flowing in the loops, which are Q 1 and Q 2. These are the position coordinates. Fine. Now, we would say that my T is the energy stored in this one, half L 1 Q 1 dot minus Q 2 dot square, plus the energy stored in this one, which is plus half L 2 Q 2 dot square. The potential here V is the 1 by twice C Q 1 square. Also, due to this, it will be minus, since it is in the direction of Q 1, E Q 1. Fine. This time there is a Rayleigh term. So, the last problem it was not there, it is only in Q 2 direction. So, it is half R Q 2 dot square. So, from here your Lagrangian is half L 1 Q 1 dot minus Q 2 dot square plus half L 2 Q 2 dot square minus 1 by twice C Q 1 square plus E Q 1. Good. So, you have it, so you can easily write the Lagrangian equation, which will now take the form, or cannot just obtain it fast, the Lagrangian way. And then I will obtain it as a first order differential equation. Done? Fine. So, keep it in your copy. Now, notice what we have done on this sheet. Here we are writing that the derivative of the Lagrangian with respect to the q 1 dot is p 1, which is nothing but this, you have already definitely done it. Similarly, p 2 is derivative of the Lagrangian with respect to q 2 dot, which is this. Now, in this case the q 1 dot and q 2 dot are not directly given. So, they are mixed up, but you can see these are two equations, and you can already very easily extract q 1 dot and q 2 dot from these two in terms of p 1 and p 2. Can't you do that? So, you will get q 1 dot is equal to 1 by L 1 plus 1 by L 2 p 1 plus 1 by L 2 p 2, and q 2 dot is equal to 1 by L 2 p 1 plus 1 by L 2 p 2. Check. From here, sorry, from here, from these two equations, we extract q 1 dot and q 2 dot. Fine. Having done so, we will proceed to write down the equations for p 1 dot and p 2 dot. Okay. So, in this case they will have to be obtained from this equation, because the r term is there. So, p 1 dot is equal to derivative of the Lagrangian with respect to q I q 1, that will come to be these two terms. So, it will be minus q 1 by c plus e. Now, we have to add the derivative with respect to q 1 dot, which is not there. So, this suffices. P 2 dot is derivative of the Lagrangian with respect to q 2 minus derivative of the Rayleigh with respect to q 1 dot, q 2 dot is q 2 is not there. So, this term's derivative goes to 0 and this term derivative remains. So, it is minus r q 2 dot, but now you have the q 2 dot in the right hand side, that will have to be substituted. So, just put it in here. So, is equal to minus r into all this stuff, r by L 2 we can write. Happy? You see, pretty simple stuff. There is no complication in this business, only if you adopt the right technique. And the crux of the technique was to properly define the additional variable. Now, let us ask this question. What did we do? We started from the Lagrangian formulation where we had the second order differential equations, then we additionally defined the conjugate momentum variables, and then using that we derive the first order equations. But ultimately, if the first order equations is our objective, why not derive them in the first order? Why not go through the convoluted route of first deriving the second order equation and then going to the first order equation? There exists a technique to do that, applicable under most situations. So, let us see that that is exactly what is known as the Hamiltonian formalism. In the early 1830s, Hamilton proposed this formalism, and that is why it is known as the Hamiltonian formalism, in which in the Lagrangian formalism we defined the Lagrangian function. What was it? T minus V. In the Hamiltonian formalism, we will define the Hamiltonian function, and in order to understand what the Hamiltonian function is, at least for most systems, if you read the books in classical mechanics, it goes in a different way, but we will go through a route that is more intuitive for the engineers, because we understand what a kinetic energy is, we understand what a potential energy is, and therefore, we understand what the total energy in a system is. Okay. So, the total energy system is nothing but T plus V, right. So, we will say that I define a function, I will write it as script H is T plus V. And then we will try to formulate Hamiltonian try to formulate the equations in terms of the Hamiltonian function, but presently we have defined what is known as the total energy function. As yet I am not talking about the Hamiltonian function. So, this is more intuitively clear to us that I am talking in terms of the total energy in the system, T plus V. Now, there is a specific property of the T term. T is the kinetic energy. It has the specific property that it is in mathematical terms is called the homogeneous of degree 2. Now, what does it mean by the homogeneous function of degree 2? What it means is that if I okay, it was T would be a function of what? Suppose it is 2 dimensional system, it is function of q1 dot and q2 dot, right. It is a function of q1 dot and q2 dot. So, it is normally and q2 dot. So, there are 2 variable velocity terms q1 dot and q2 dot, and this one is a function of that. The question concerns what kind of a function is it? It is that kind of a function, so that if I multiply the q1 dot and q2 dot both by some number k, that means I just scale it up or down by some number k, then the T, yes, it will be reflected as k square times T right. So, any function that obeys this property is called a homogeneous function of degree 2. And there are some mathematical rules that these homogeneous functions of degree 2 follow, and we will use that. So, what is it? Suppose I now differentiate this equation with respect to k. What do you have? We will first say I am differentiating this with respect to k, then first I will have to differentiate with respect to k q1 dot, and then k q1 dot with respect to k. So, what do we have? We have q1 dot times derivative of t with respect to k q1 dot, that is the first one, chain rule. So, the second term will be derivative of t with respect to k q2 dot, right. So, I am differentiating with respect to k using the chain rule. It is a function of two things. So, I first differentiate with respect to this, and k q1 dot with respect to k, that yields q1 dot, and similarly the next one is equal to, in the right hand side what you have, twice k t fine. Now, this is again a property of the homogeneous function of degree 2, this equation, and k being arbitrary, we could choose any k, still this equation will be valid. If we choose k is equal to 1, then also this equation will be valid. Okay, choose k is equal to 1. So, for k is equal to 1, it will become q 1 dot derivative of t with respect to q 1 dot plus q 2 dot derivative of t with respect to q 2 dot will become equal to twice t q 1 dot q 2 dot. So, if this is true for two variables, we had assumed q 1 dot and q 2 and q 1, these are the two variables. If there are n number of variables, it will be the same. After all you have to do is to expand this in a longer chain. So, in general we can write that this left hand side will be summation of q I dot how many n, and this side is twice t. Okay. Now, this result is known as the Euler's theorem, that goes by the name of Euler. Now, notice that this term t okay. So, we already know that the v term is normally independent of potential is not dependent on the velocities, at least normally. We will come across situations where it can be, and in those cases we will have to exercise some caution in deriving the differential equations, but for many systems, most systems, this is true. If this is true, then if this is so, then we can write the Lagrangian here. That is what we did earlier. So, this yields summation over n q I dot derivative of the Lagrangian with respect to dot is equal to twice t. Okay. So, this result we will use, just keep it in hand for now. Now, we have said that we want to deal with the total energy function H, which was T plus V. Fine. We will write it as twice T minus T minus V. Okay. Twice T we know what it is, T minus V we know what it is. So, substitute, you get sum over I q I dot derivative of the Lagrangian with respect to q I dot, that is what is the twice t term minus the Lagrangian itself. Fine. And this term also we know. What is this? The pi, right? This term is nothing but pi. So, we can write q I dot p I minus L in the right hand side. Now, it so happens that this term this term in the right hand side is known as the Hamiltonian function. Hamilton actually defined this function and showed that it is actually the same as the total energy function T plus V. But we had started from the total energy because for us it is a more intuitively appealing quantity, and we showed that the opposite, the total energy is nothing but this function, but either way it is the same thing. Now, notice this, we have this equation as the total energy.
So, over here we have assumed Rayleigh function to be 0.
No, not yet. There has been no use of the Rayleigh function at all, because Rayleigh function does not contribute to the total energy. Energy is nothing but kinetic energy plus potential energy. So, Rayleigh function is entirely different affair. It does not contribute to the total energy content of the system, just two components. Clear? We will introduce the Rayleigh in the right place, do not worry. We are not ignoring that. So, this is the Hamiltonian function. Now, so we have two things. In the left hand side we have the H function, and in the right hand side we have the Hamiltonian function. Okay. And in our nomenclature we had called this term as something like script H, because this in concept represents the total energy, and the Hamiltonian H is normal H is this. We just showed that the script H that we started with is equal to the Hamiltonian H. Good. Now, what is this total energy dependent on? Total energy is dependent on the momentum, the position and the time. Okay. So, we can write the total energy H is a function of P I, Q I and time, right. That stands to reason. The momenta are dependent on the kinetic energy dependent on the momenta, and the potential energy dependent on the positions, and things can be dependent on time also. If that is so, then if we take a differential of it, we can write dH as, if it is it is dependent on three things, then we can expand it by the chain rule to obtain sum over I. It will be the first is partial derivative of H with respect to P I, then d P I plus the partial derivative of H with respect to Q I d Q I plus this time it will not be a summation, these two are summed over, this will just be the term which is the partial derivative of H with respect to T, and this will be dt. Fine. So, this is how this term expands. We have seen that this is also equal to this term, right. So, we can also expand this term in the same way. Let us see what it yields. Let us keep it here. We have seen that the H is also I Q I dot P I minus the Lagrangian, and now I want to write it as H. How will I write it? First, you have this term here, it is dependent on Q I, dependent on P I, dependent on L. So, we have to write taking the derivative of this, it will be Q I dot d P I, and that will be summed over I plus again Pi dqi dot, that is also summed over I. Okay. These two yield the derivative of here, and now this Lagrangian we know is a function of qi dot and time. We have already seen that. So, it will have to be written as minus derivative of the Lagrangian with respect to qi, it will be dqi also summed over I, minus derivative of the Lagrangian with respect to qi dot dqi dot again summed over I, and time it will not have to be summed over, it is derivative of the Lagrangian with respect to t, sorry, that completes the story. Now, notice there are two terms involving dqi dot, and we can take them common. So, if you take them common, you have the first term qi dot dpi plus first let us take them common, it is summed over I dqi dot, and then inside the bracket it will be pi minus delta Lagrangian of, that is qi dot, then the rest of the terms remain. Now, notice what is this? Will be 0, yes, because this is nothing but this. So, this whole term goes to 0, simplifies our affair. So, it is only this, this and this. So, write it down. dH now yields I qi dot dpi minus now we already have this equation, right, and from here we know this term. We had already obtained this, and from here we know this term. So, we let us write down your derivative of Lagrange with respect to qi is, now here we are including, can you see that?
Yes,
we are including this, yes. So, it is pi dot plus dot. So, let us substitute it here. You have dH minus this term, it will be okay. Let us start with plus, and I, it will be minus pi dot minus derivative of the Rayleigh with respect to qi dot. It will be dqi minus Lagrangian del t dt. Okay. Happy? Well. Now, you see we have obtained this from the right hand side, and this was another equivalent expression we had obtained. In this case, we had stated that H is dependent on Pi, Qi, T, and we had expanded this, and in this case we had written that that is also the Lagrangian function, and therefore, we have expanded that. In one case we had obtained this, another case we had obtained that. Now, notice that they are almost the same, only here is a term that summed over I Pi term, summed over I Qi term, summed over I T term. Obviously, this term and that term should be the same, this term and that term should be the same, and this term and that term should be the same. Okay. Do you see how simply it becomes? All this mathematics ultimately then yields three very simple results. The first thing is Qi dot will be equal to then this minus Pi dot minus will be and fine. Normally in books you will find these terms written in the left hand side and these terms written in the right hand side, but I have chosen to write it this way because ultimately what we want to extract are these two. We will do that, but let us understand this. This is a differential equation first order, this is a differential equation first order, this is not a differential equation. This only says that if the Lagrangian function is independent of time, the Hamiltonian function will also be independent of time, and if they are dependent on time, they are dependent this way, that is all. But this is not a differential equation, therefore, it does not really define the dynamics. We are primarily then interested in these two equations, and these two equations immediately yield Qi dot is equal to derivative of the Hamiltonian with respect to Pi, and Pi dot is from here I am trying to extract it, it is this minus that is it. That is what the Hamiltonian equations are, first order, nice shape, clear. We will illustrate how to apply this to physical systems, definitely that is what we are doing always. We derive a formalism and illustrate it with a large number of examples, do not worry about it. But notice one thing, that if this term is ignored, that means if some system does not have this term, for example, the spring pendulum and stuff, then it takes a very nice symmetrical form. Can you see that? Very nice form. Qi dot is nothing but the Hamiltonian derivative of the Hamiltonian with respect to Pi, and Pi dot is nothing but the derivative of the Hamiltonian with respect to Qi with the negative sign, that is all. Very nice set of equations. That is why this has intrigued physicists for a long time, and many physicists have devoted their lifetime studying this nice set of equations. And if this is ignored, what you have, that kind of systems where such equations will be valid are called the Hamiltonian systems. Okay. So, the Hamiltonian systems are that is it, where the Rayleigh term does not exist, which means there is no dissipation or friction, then you have got Hamiltonian system. Remember, such systems are actually very important. Supposing a scientist is studying the motion of Mars, obviously that is a Hamiltonian system. The friction dissipation is very small. If one is studying the motion of electrons in a atom, Hamiltonian system, we do not have any concept of friction there. So, these things are not really imagination. This being ignored actually happens, but for our purpose, since we are primarily interested in engineering systems, we will include this, except for a few exceptions which are also not really coming from engineering, but our exercise to understand such systems, the spring pendulum and all. But for most engineering systems, there will be some kind of friction or dissipation. So, we will include this. Good. Remember, in other books you will not find this equation with this term, only I am including it, so that you can derive the equations using this formalism. Fine. So, we have these equations, and then we need to understand how to obtain the equations with this. Let us go back to the circuit example that we took today. Where was it? Circuit example was here. Here was the circuit example we took. So, here we have already written down the T, we have written down the V, and we have written down the R. Notice that in the Hamiltonian formalism, we need to write down the right hand side, and right hand side means H as derived in as taken derivative in terms of Pi, H as taken derivative in terms of Qi. So, H has to be expressed as right, it has to be expressed as Pi. The problem is that if I simply write it as T plus V, it is expressed in terms of Qi dot, not as Pi. So, the first task will be to express it in terms of Pi. Clear? So, that is what we have to do first. In this case, in this particular example, H is T plus V, and let us write down T plus V first, using the expression for the T and the V that we have already written. We will say half L Q1 dot minus Q2 dot square plus half L, sorry, this is L1, this is L2, Q2 dot square, and the other terms will be now plus. Remember, T plus V, 1 by twice C Q1 square minus E Q1. Fine. Now, we need to express this in terms of the Pi's. Now, we had already obtained this, right, and this. So, we can substitute. So, if you substitute these here, we get where is it? This term is P1 by L1, this term. So, we can easily express half L1 P1 by L1 square, fine, plus half L2, this is P1 plus P2 by L2 square, plus the rest remains the same, square C Q1 square minus, fine, we are done. So, we will just simplify it to twice L1, because L1 goes square here, P1 square plus 1 by twice L2 P1 plus P2 square plus 1 by twice C q 1 square minus E q 1. So, that is how we have derived H in terms of the P's and Q's. Happy? The rest is algorithmic. The rest is algorithmic. We will say simply that the derivative of H with respect to P 1 is nothing but Q 1 dot, simple, and this immediately yields P 1 by L 1 plus P 1 plus P 2 by L 2. Similarly, Q 2 dot is derivative of the Hamiltonian function with respect to P 2, which is P 1 plus P 2 by L 2. Okay, just check. Now, P 1 dot is minus derivative of the Hamiltonian with respect to Q 1, which is these two terms appear. It will be minus Q 1 by C plus E, done. P 2 dot is well, in the sorry, I did not include the Rayleigh term, but in any case the Rayleigh term does not depend on Q 1 dot. So, even if we should have written it here, we are not wrong. This is minus derivative of the Hamiltonian with respect to Q 2 minus Rayleigh with respect to Q 2 dot, that becomes this is 0, this remains minus R Q 2 dot, and then you substitute minus R by L 2 P 1 plus 2. Okay. So, that is how you write down the differential equations. Simple procedure can be applied and can be applied to most systems. Most in the sense that we had made some assumptions while deriving the Hamiltonian equations. If some system violates them, then we have to exercise caution. Otherwise, this simple procedure works. Okay, we will continue in the next class.